We are discussing chapter number 2, which is electrostatic potential and capacitance. The potential energy of a dipole in an electric field. So we have seen about the electric dipole, what is the uh, electric field of a dipole, equatorial axis on the axis of the dipole, we have already seen. But we are about to see the potential energy of this dipole in an external electric field. So we are interested in potential energy. So if you see here, this is an electric dipole. We have A here, B here. So at A there is a minus Q charge, at B there is a plus Q charge, and the distance between this A and B, this AB, is 2A, right? Now this electric dipole is placed in uniform electric field. You can see that these lines are equidistant. So this shows that this is having a uniform electric field E, and the direction is X. The direction is X. That means the axis of the dipole makes some angle. Say let's make some theta. This theta angle, this one. This is dipole. This is electric field. This is the theta angle they are making. So its dipole moment will be simply Q into 2A. We know that the charge is Q, the distance is 2A, the dipole moment will be Q into 2A, and the direction will be in this direction, AB of the dipole. The electric potential energy of this dipole, what is this? This is will be the algebraic sum of the electric dipole energies of both of these charges, minus Q and plus Q. What we will see, will take arbitrarily the potential at the position minus Q as 0. So its potential energy, we are just taking it. You will just know that why we are taking it. We are taking the potential here at the position minus Q as 0. So the potential energy also becomes 0. Now we will try to find out the potential energy of this plus Q with respect to this minus Q, and this will become the potential energy of the whole dipole. The electric field is only in X direction. So what, as you see here, electric field is only in X direction. So what do we get here? Electric field E is given by minus del V by del X. And what is this del V? Del V is the difference in potential between this A and B because of these two charges. So del V will be VB minus VA by the delta X. Delta X is nothing but the distance like this here. And we are going to see AC. You will be amazed that we have to take this distance, but we are not taking this distance, but AC. AC is the distance because the electric field is in this direction and the dipole is in this direction. So we have to take the cos component of this, that is AB cos theta. This is AB is 2A, this is theta, so this will be 2A cos theta. This distance we have to take between Q minus Q and plus Q because we need to take this in the direction of E. So we will take AC as 2A cos theta, and we have arbitrarily assumed that this VA is 0. So this becomes only minus VB by 2A cos theta. So what will be VB? Just take this on this side. So VB becomes minus E into 2A cos theta. This is the potential VB. Now how to find the U, that is the potential energy? This can be found out by just multiplying this charge Q with VB. Potential energy is Q into the potential. Potential energy will become Q into VB. VB just found to be minus E 2A cos theta, put it here. And this Q, bring Q and 2A together, and this Q and 2A is nothing but the dipole moment. So we can write E. So what is this? E P cos theta. And what is this E P cos theta? This has to be E dot P, because E dot P, the dot product is E P cos theta. So this U becomes E dot P and minus sign. So the potential energy because of this entire dipole is nothing but minus E dot P. This is the value. So what we should note here, because cost is involved, so the axis of the dipole is normal to the electric field, that is theta equal to pi by 2. That is, this is electric field and this is the dipole, say minus q plus q. This is 90 degree. So when this is 90 degree, this E dot P will become EP cos theta. Theta is 90 degree. So cos 90 is 0. So this potential energy of a dipole becomes 0. And if it is parallel, say if this is the electric field line and this is the dipole, say this is minus q, this is plus q, the axis, because they are making 0 angle with each other, that will be cos 0 here. It will be simply theta is 0, so simply it will be minus PE. The axis of the dipole is parallel to the field. AB is parallel to E here. If you see, AB, if it becomes parallel to this AC, then the dipole will become just simply minus PE. Now, if this has become minus PE, this is the minimum value of potential energy. So dipole actually tries to arrange its axis parallel to the electric field. Everything wants to be equilibrium and gain or have minimum energy. So it will try to align to the direction of the electric field. So this dipole moment P becomes parallel to E. So this, in this state, we say that the dipole is in stable equilibrium when the axis of the dipole and the electric field dipole, or the electric field on this dipole, they are parallel. As I just said, any system will always try to remain in a state where the potential energy will be minimum. If you make theta equal to minus pi, that means if this is in this direction, means if you rotate this, plus q here, minus q here, then it will be in unstable equilibrium. So we have to see about the charge also, because we have to understand that the electric field is in which direction. Electrostatics of conductor. Now, when a metallic conductor is placed in electric field, or when electric charges are placed on such conductor, what are the effects? What are the attributes and characteristics that we are able to see? So the effect of external electric field on any conductor will be what? If we have a metallic conductor. So in metallic conductor, there are positive ions which are situated at the lattice points, and there are free electrons. They are moving randomly. These electrons, they move randomly between these positive ions, and they are free to move in metal, because we know that in a metal there are free electrons. That is why they conduct electricity. But they don't come out of the metal. They move inside the metal. When this type of conductor or any metallic conductor is placed in any electric field, say E dash, the the free electrons, they move under the effect of the force which is in the direction opposite to the field. And what will they do? They get moved or deposited on the surface of on the end of the conductor, and an equal amount of positive charge, because if negative charge is located or is placed at one point, the same amount of positive charge we can consider it to be deposited at the other end, right? Because the charges are same. So the electric charges are induced. And these induced charges, they produce an electric field by itself, E double dash. The metallic conductor is subjected to an electric field E dash. Because of this, there is induced charges. Induced charges, they produce another electric field inside it, which is E double dash, and which is in the direction which is opposite to the electric field E. And when these two electric fields, they become equal in magnitude, that is, the resultant electric field E will become 0. I'll show you with this diagram. The motion of charges in the conductor would stop, and the charge becomes steady or stationary on the end. So what is happening here is, there is an E dash electric field this metallic conductor is subjected to this E dash. Because of this, the charges are deposited here, and you can say there are induced charges. Because of this, there is an electric field E double dash. Now E dash is in this direction. E double dash, because of the charges inside the metallic conductor due to the electric field outside, there is E double dash, and E dash and E double dash are in opposite direction and they are similar in magnitude. The resultant electric field will be 0. Now the charges are stationary. Let us say that we have a Gaussian surface, and this is the dotted. If you see this, we have a dotted line, and this is a Gaussian surface inside this conductor and very close to this surface. Every point on this surface is a point inside the conductor here. So the electric field E on this entire surface will be 0. The electric charge enclosed by it also 0, because we have discussed it, what is happening here. So the because why electric charge will be 0? Because electric E dot dr is equal to q by epsilon naught. So if this is 0, this is going to be 0. So in this case, the metallic conductor, when we place it in electric field, a steady electric charge distribution is induced on the surface of the conductor. So if this is, say, a conductor, it is subjected to some electric field. So there is a steady charge which is induced inside the surface, or you will see it on the surface of the conductor. The net electric field inside this conductor will be 0. Electric field will be 0. Electric charge would be 0. And on the outer surface of the conductor, the electric field at every point is normal, locally normal. Here it will be like this. So locally normal to the surface. If the electric field were not normal, that is, it is not perpendicular, then we have to take the component. If it is not like that, if it is like this, so we have to take the normal component of electric field which is parallel to the surface. There will be components, and due to which the charge would move on the surface. But I am saying that the motion is stopped. The charges have become steady. So the component of electric field which is parallel to the surface would be 0. The electric field would be normal to the surface. Okay. Because of the two fields which are nullifying each other, since we are saying that the E is 0 at every point inside the conductor, the electric potential everywhere inside the conductor will be constant. See, because of electric field is 0, electric potential will be constant. And what will be the value? It will be the equal value as on the surface. So if there is, say, some cavity inside, the conductor, then even when this conductor is subjected to some external field E dash, the net electric field inside the conductor will again be 0. And inside this cavity will also be 0. Because just consider this dotted, see, there is a dotted Gaussian surface. Since every point on this surface is a point inside the conductor, this is inside this conductor, this is inside this is a conductor, and every point here is inside the conductor, the electric field on this entire surface will be ultimately 0. So the total charge will also be 0 in this cavity. We know that E dot, you take a very small part because this is a cavity. So E dot ds, if it is equal to q by epsilon, so we can safely say that the total charge on the surface of the cavity will be 0. And there is no charge inside this cavity, there is nothing inside. So the electric field everywhere inside the cavity will be 0. And what is this? This is known as electrostatic shielding. What is this called? Electrostatic shielding. See, if we are sitting in a car and say some lightning strikes, we would close the doors of the car, and we suppose the car is fully made of some metallic conductor, and by doing so we are in the cavity inside the car, and then because of this electrostatic shielding we are saved from the lightning effect. What are the effects being produced by putting charge on the conductor? So this is a conductor. So this is the conductor. We, in the previous discussion, we considered the effects produced when a metallic conductor is placed in external electric field. Now we want to know the effects produced when a charge is placed on a metallic body. There is no external electric field. There is no external electric field. We are just saying that we want to know the effect when a charge is placed on a metallic body. So whether a metallic conductor is put in an external electric field or not, or whether a charge is put or not on it, in all these conditions, the electric field everywhere inside the conductor here will always be zero. This is a general fact, and you can just take it as a property in order to define a conductor. Now the charge placed on a conductor is always distributed only on the outer surface, say here, only on the outer surface of the conductor. So we can understand this by the fact that the electric field inside that conductor is zero. So we can have a Gaussian surface. You can show it by some dotted surface. Every point on it is inside the surface. If you just take very small, I am taking here. This is a dotted surface. Now this is inside. Every point on it is inside the surface, and it is not on the surface because the charge is on the surface. So the electric field at every point on this surface is going to be zero. So according to the Gauss theorem, the charge enclosed by that surface will also be zero. If you see here, we are just taking a very small portion, and we are just saying that the charge is only on the surface of the conductor. If you take a stable condition, these charges are steady on the surface. So this is showing that the electric field is locally normal to the surface. And the electric field at any point on the charge surface, electric field is given by, because this is a proper surface, so we have to take sigma. Sigma by epsilon naught, n cap is the unit vector coming out from the surface, which is normal or perpendicular to the surface. So in order to prove this, we will consider or will take a Gaussian surface, say of a pill box, or this is a pill box. If you see it very closely, it's a very small one we have made. It's a cylinder, and we consider it to be extremely small length, having small length and extremely small cross section ds. So very small length and cross section surface ds. Let me enlarge it for you. This is a cylindrical surface, right? And a fraction of it is inside. It is inside the surface, and some of it is and fraction of it will be outside the surface. So the total charge enclosed by this box, we are calling it is as a pill box. So we know that this sigma is nothing but Q by area. Q is equal to sigma into area. So Q will be sigma into A. We are taking it as ds, very small cross section ds. So Q will be sigma into ds. Sigma is the surface density of charge on this conductor. It is the surface density of the charge we are placing on this conductor. So at every point on the surface of the conductor, this electric field will be perpendicular. See, if you see, it will be perpendicular to the local surface element. So it will be parallel to the surface vector. So we said that electric field will be parallel to this ds. If you see, if ds, this is a cross section, this is ds, this is electric field. So they are parallel. They are parallel to each other. But when you go inside the surface, inside this, so we are taking this portion now. Inside this, electric field will be zero. So the flux which is coming out from the cross section of this pill box inside the surface here will be zero. And from its side, the area vector, you can say a surface vector, is normal to E. It is normal to E. If you see this, it is normal to this electric field. And electric flux through it will be zero. So the flux which is coming out of the cross section of pill box, which is outside the surface, will be E dot ds, which is E ds. We are talking about this. The total flux will be eventually E dot ds only. And according to this Gauss theorem, we know that E ds will be equal to Q by epsilon naught. Q we can write it as sigma ds. So we are writing sigma ds by epsilon naught. So what E becomes? Ds gets cancelled. Electric field will be sigma by epsilon naught. you want to write it in a vector form, you have to put n cap. So if this sigma is positive, E electric field is in the direction of normal coming out of the surface. If sigma happens to be negative, electric field is in the direction of normal, which is entering into the surface, right? Into the surface. If some charges is placed inside the cavity of the conductor, say inside this, there is a cavity. So if some charge is placed inside the cavity of the conductor, then the charges are so induced on the surface of the cavity here and on the outer surface of the conductor that the electric field in the region which is inside the conductor but outside the cavity will become zero. So electric field inside the cavity is non-zero, and the electric field outside the conductor due to that charge is also non-zero. There are certain things which we can discuss. The sharp ends of the conductor, they have large electric charge density, because there can be multiple type of conductor. The electric field near these sharp ends are very strong, and these strong electric fields can strip the electrons from the surface of the metal. So the electrons may come out because of the sharp edged part. If this is the sharp edge, and this is known as corona discharge. This is known as corona discharge, and we call it as dielectric breakdown. What we call dielectric breakdown. And the electron which are escaping out or escaping from the surface of metal, they perform an accelerated motion. They collide with the electric particles or air particles coming in their way, and the excited atom of this energetic particle, they will emit the electromagnetic waves, and you'll see a greenish glow. And apart from this process, the ionization of the air molecule also takes place during collision, because this is a sharp surface, electron is coming out, there is air, so there is some form of, because there is a collision, so there will be some ionization. And sailors long ago, if you take past, saw these glows at the pointed tops of their masts and spars and dubbed the phenomena, right? St. Elmo's fire. So this is for information only. Capacitors and capacitance. What is capacitor and what is capacitance? Just consider an insulating conducting sphere as you see here. Suppose we go on gradually adding some positive charge on this sphere. This is a positive charge and this is just a conductor, or it is insulated, there is an insulation. This is a non-conducting stand. So we are gradually adding some charge, say positive charge on this sphere. This is a sphere. So as this charge on the sphere is increasing, we are increasing the potential V on the surface of the sphere, and the electric field around this sphere will also increase. We are increasing the charges, so because of this, the resulted effects, the potential and the electric field is going to, by nature of the properties, it will increase. So in this process, at certain stage, the electric field becomes sufficiently strong in order to ionize the air particles which are around the sphere. Now because we are increasing the charges, at some point it is going to affect the air particles, okay, and the insulating property of air gets destroyed because it cannot be sustained. We are putting a lot of charge here, and this is known as dielectric breakdown. The charge on the sphere will be leaked. It will be leaked, and now the sphere will not be able to store any additional charge. Even if you put the charge again and again, or more charge, that sphere will not be able to sustain. And in this entire process, the ratio of the charge Q on the surface or of the sphere and the potential V on the sphere will always remain constant, and the ratio is known as the capacitance. What is the capacity of any conductor or the conducting sphere to sustain a charge? So this C, which is Q by V, this Q by V, it will always remain same, and this is nothing but the capacitance, right? The ratio of charge to the potential is the capacitance. The maximum capacity beyond which it is not going to sustain. It will the electron will come out, or it will ionize the air particles, air molecules outside. So the maximum electric field up to which an insulating, say a non-conducting medium, can maintain its insulating property is called the dielectric strength of that medium. Or the minimum electric field which start ionization in a given non-conducting medium is called as dielectric strength. So this is the dielectric strength. For air, this dielectric strength is around 3000. Now, if we want to increase the capacity of this sphere to store charge, say capacitance C, then place another, say some conducting sphere, this sphere, some other conducting sphere near the first one. So electric charge will be induced in the second sphere. Say if this is sphere, this is plus charge. The negative will be attracted here, the positive will be deposited here. Now we can just put a ground wire here, and this positive charge will be gone. So if the second charge is, as I said, the second charge is connected to Earth, the electron from Earth will flow to it and neutralize this positive charge. Electron are going to come here and they are going to neutralize this positive charge. Now, due to the negative charge on the second sphere, this potential on the surface of the first sphere and the electric field near it will be decreased. Now, the capacity to store charge on the first sphere will increase as compared to earlier. So, in this scenario, the ratio of Q, electric charge, and the potential difference between these two spheres at every stage will always be constant. And this is ratio is called the capacitance of this system of two spheres. One sphere, two sphere. And this is a system of spheres. So the ratio of capacitance, the ratio of Q by V, which is the capacitance of these two spheres, will always remain same. And this capacitance depends also on the dimension of these spheres, what is their relative arrangement, and what is the medium between them. So a device which is formed by two conductors insulated from each other is called as a capacitor. What is a capacitor? We just saw an example. So a device which will be formed by two conductors insulated from each other is known as a capacitor. And these conductors, they can be called as plates of capacitor. And the conductor with positive charge is called the positive plate, and one with negative charge will be called as a negative plate. And the charge on the positive charge is called the charge on the capacitor, and the potential difference between these two conductors will be known as the potential difference between these two plates of the capacitor. So the capacitance of a capacitor C is given by charge by potential difference. What is the SI unit of capacitance? It is coulomb per volt. C, it is coulomb per volt, and because of the great scientist Michael Faraday, it is known as farad. Symbol is F. Farad is a large unit for practical purposes. So we use microfarad. Micro is 10 to the power minus 6. Nanofarad 10 to the power minus 9. N is 10 to the power minus 9. And picofarad, which is 10 to the power minus 12. So capacitor having say some definite capacitance will be shown like this. There will be a line, there will be two parallel lines, and this. These are representing the plates. And the one which is having a variable capacitance will have a arrow like this. A single conducting sphere, say of radius r, and it is having, say, charge q, this can also be considered as a capacitor, a single conducting sphere. Why? Because it has some capacity to store charge. And for such a capacitor, other conductor minus q will consider that it is at infinite distance. Minus q is at infinite separation. And we take the potential at infinite distance from the sphere as 0. So the potential on the surface of a single sphere V is given by K into Q by R. So the potential difference between these spheres and the other one, which is imagined at the infinite distance or separation, will also be V equal to KQ by R. So the capacitance of the sphere we are talking about, C, will be Q by V, and if we put V as kq by r. This gives you qq cancel, r by k, and k is what? 1 by 4 pi epsilon naught. So k is in the denominator, it becomes 4 pi epsilon naught r. Earth is considered as a capacitor. Parallel plate capacitor. These are two plates which are placed parallel to one another. So in this type of capacitor, there are two conducting parallel plates, say this one and this one, of equal area, and they are insulated from each other, and they are at a distance of d from one another. Just consider a vacuum or air as the non-conducting medium between these two, and we'll try to find out the formula for the capacitance. Now suppose that electric charge on this capacitor is Q. The value of the surface density of charge on it will be sigma will be Q by A. Let us say that A is the area and Q is the charge. So sigma will be the surface charge density. Surface density of the charge will be sigma Q by A. D is the distance between them. So D is kept very small as compared to the dimension of each plate. Because of this, the non-uniformity of the electric field near the ends of the plates we can neglect. Otherwise, if the distance is large, it will be considerable. And the entire region between the plates of the electric field E, we can take it as constant. So the uniform electric field in the region between two plates due to positive plate, we know, we have already learned this. So the electric field, because of a plate or uniformly placed charged plates, is nothing but sigma by 2 epsilon naught. This is in the direction from positive to negative. The uniform electric field in the same region due to negative plate. This is because of positive plate. Because of this positive plate, it will be sigma by 2 epsilon naught, this one. And because of this negative plate, it will be sigma by 2 epsilon naught because of this negative plate. And this direction will always also be in the same, means positive to negative plate. Now we got this E1 and E2. So these two fields are in the same direction. So we can just, this is direction, same direction, we can add them. So E1 plus E2 will be sigma by 2 epsilon naught and sigma by 2 epsilon naught. We can add, it will be sigma by epsilon naught. And this is in the direction from positive to negative plate. So this eventually comes to be, because sigma is Q by A, we can write sigma by Q by A here. So it will be Q by A and epsilon naught. So in the region on the other side of the plate, here or here, E1 and E2 will be in the opposite direction. So the resultant electric field will be 0 because the direction will be opposite. If the potential difference between these two plates, say from here to here, it is V. We know that V will be equal to E into D. D is the separation, E is the electric field. From this equation, we can just write V as E into D. E is, we can write like this. We can take it here. It will be Q by epsilon naught A D. And we also know that C, the capacitance, is Q by V. So we get the capacitance of a parallel plate capacitor as what? Just put this V here now. So Q by V, the things which get cancelled, C will be epsilon naught A by D. So very clear from this expression that if the distance between two plates, capacitance is inversely proportional to distance. So if the distance between two plates, say, just take some measurement, 1 meter by 1 meter, the distance is 1 millimeter, the capacitance will be, we know the epsilon naught, we know the A, we know the D, just put it here, it will be 8.85 into 10 to the power minus 9 farad. So if we want 1 farad capacitance, then the area of each plate, which is kept at a separation of say 1 mm, should be what? Area should be, we need to find out the area now. So this will be C into D by epsilon naught. Just put it here, it will be this much. So each of the length and the breadth of each plate should be nearly 10 kilometer. See, this is what we require. And this is just an idea that we'll be using this in solving the questions so that we understand what is the electric field, the potential and the capacitance between these two plates. Combinations of capacitor. There are different capacitors, they can be placed in various combinations. So if we have capacitors, say C1, C2 and Cn like this, they have some equivalent effective capacitance. If you combine them, if you arrange them, there will be a equivalent capacitance. So we'll try to discuss most oftenly used combination, series combination of capacitor, and the arrangement is found by joining these C1, C2, Cn by conducting wires. These are the wires and they are connected, they are joined like this and they are in series. So one is like this, the other is in the series of the other. So like this. So this one, first one has say potential V1, charge Q, and C1 is the capacitance. Likewise for others. This is a scenario of series combination of capacitor. In this condition, the charge on every capacitor has the same value, all has Q. A minus Q charge is deposited by the battery on one plate because this is a battery, so minus charge will be here. So it will induce a positive charge here. See, there is a positive charge induced here. This minus Q charge from second plate will be deposited on the near plate of the next capacitor. Because of this, because this negative charge has been induced, this plus will be there. Because of this negative, this will be positive. Because of this positive, this negative. Because of this negative, there will be a positive charge because of the attraction. So this induces plus Q charge on another plate, and this goes on and on as you see here. So all capacitors they will have equal charges, but the potential difference between these two plates of different capacitor means if these are two plates, the potential difference here will be V1 and for other it will be some different value. So we say that V1, V2, V3. So from if this is the whole potential V of the battery, this V1, V2, V3 will be added and this will be equal to V. This is the total potential being provided by the battery. So we say V will be equal to V1 plus V2 plus V3 till Va. And what is V? V is Q by C1. We know that capacitance is simply Q by V. So for V we can write Q by C. So Q by C1, Q by C2, Q is equal or similar. C1, C2 varies. This V can be written as this V can easily be written as, because this is the charge Q. Let us take it here. Take it outside. All this Q can be taken outside, means one Q can be taken outside and it can be brought down with V. So V by Q will become 1 by C1 plus 1 by C2, 1 by C3 till 1 by Cn. What is this V by Q? We know that C is Q by V. So what is V by Q? It will be equal to 1 by C. So 1 by C will be equal to 1 by C1 plus 1 by C2 plus 1 by C3 till 1 by Cn. So the value of the effective capacitance is even smaller than the smallest value of the capacitance in the combination, right? And this is very equivalent to the resistance which we obtain in the parallel combination of the resistances. Parallel combination of capacitor. So these are the capacitor, we are putting them in the formation so that they are in parallel. This one is here, the other is here, third is here, like this, and they are having a proper equal potential difference between them. So this is A point, B point. In this type of combination, the potential difference between the plates of every capacitor will be same because the potential difference is same, plus plus plus. Because of this minus, this plus is being induced, and everywhere the potential will be same because they are between A and B. All of them are between A and B, right? The charge Q will be different. Say here we have charge Q1, Q2, Q3. So what will be Q? We know that C is given by Q by V. So Q will be, for first one will be C1V, capacitance of C1. The potential difference, as I said, will be equal. Q2 will be C2V, Q3 will be C3V. And because this Q is distributed into Q1, Q2 and Q3 like this, so Q will be equal to Q1 plus Q2 plus Q3. This we can do. Q is equal to Q1 plus Q2 plus Q3. In place of Q1 we can write C1V like this, C2V, C3V. Take V outside, so C1 plus C2 plus C3. And take V in the denominator of Q or the left hand side, you get the effective capacitance of this parallel combination. C will be given by Q by V, which is C1 plus C2 plus C3. If you take, these are only three capacitors, you can just generalize it to for multiple capacitors. So it will be C1, C2, C3 and till Cn. So the values of capacitance are added to the value of effective capacitance. This is even larger, greater than the largest value of the capacitance in the connection. And this formula is again, the parallel combination is similar to the formula for the effective resistance we found out in the series combination of resistances. So see, there is a variation. In capacitance and in resistance, the things changes. Prove that the force acting on one plate due to other in a parallel plate capacitor is this much. We have known that the electric field due to one plate, if there are two plates like this, the electric field E1 is sigma by 2 epsilon naught. A second plate having a charge say Q into A is present in this field, right? The force which is acting on this second plate is F will be sigma A into this electric field. We can substitute this value here. F will be equal to sigma A, and in E1 we will place this one. It will be sigma square A by 2 epsilon naught. But we know that sigma is charge by area. We can put sigma as Q by A. Just put it here. It will be Q square by A square. Just resolve it and you'll get. And see, the capacitance is epsilon naught A by D. So we can write epsilon naught A by D, this one, as capacitance. So we are writing capacitance. Also, this Q can be written as CV because C is Q by V. So put CV here. So it will be C square V square, and this 2 epsilon naught means epsilon naught A by D will be C, and this get cancelled, so it will be eventually this value only. This is the force. This figure is showing infinite number of conducting plates. There are infinite numbers of conducting plates of very, very small, infinitesimal thickness, and such that the consecutive plates are separated by a small distance dx, which is spread over a distance d. From this d, very small distance dx is there. We have to calculate the value of capacitance in this type of arrangement. So the capacitance of each of the capacitor in this arrangement will be what? Well, let us take, we know that C is epsilon naught A by D. If we are taking very small charge, we will take very small, this distance is very small, dx. So it will be dc will be equal to epsilon naught A by dx. And this all capacitor can be assumed to be in series with each other, right? So 1 by C will be equal to 1 by dc plus 1 by dc. All have, this C, dc we can use because in the question it is given, all have equal attributes. So 1 by dc plus 1 by dc, like this, it goes on and on. And it in this dc we can write epsilon naught A by dx. So let us write it. Here this 1 by epsilon naught A can be taken as outside. This dx plus dx plus dx remains, and if this dx can be added, if this is dx, this is dx, this is dx, if we add this dx, all dx, it will give you d, nothing but d. So 1 by C will be equal to d by epsilon naught A, C will be equal to epsilon naught A by d. And this is equivalent to the capacitance of the capacitor formed by the first and last plate in this arrangement. So this is one more installment of this discussion. We'll be taking one more. Till then, thank you so much and take care of yourself.